Yeah, it's been a great workshop. I'm sorry I only got to be here for the second half of it, but I saw a bunch of the talks, even the ones I weren't here for, and really enjoyed interacting with all of you. And it's great to be back at IPAM. I remember, um, as I think Tom Griffiths mentioned, others, we started organizing some workshops on computational models of cognition here almost 20 years ago, and I have really fond memories of this room. Okay, so I'm going to be talking about scaling intelligence the human way. And for a talk that's after lunch and at the end of a week, an intense week, I thought I would start it off in a slightly lighter way and just give a sort of high-level talk, although there'll be a lot of specifics, and I'm sure I won't get to all of it, but we'll adapt, and really looking forward to interacting with you. And also, if we don't get time for all the questions and things, I'll be around after. So I'm a computational cognitive scientist. I think about how the mind works in computational terms, but I'm also an AI researcher, and I think the best way to constrain and guide our theories of cognition is also to make our theories of cognition models of AI. And reflecting on the amazing progress that we have in AI today, very much in the spirit of this entire workshop, I think it's really striking, right? We have robots that are out there in the world making life or death decisions, for real, right? I mean, otherwise known as self-driving cars. They save lives, they take lives. Hopefully, they save more lives than they take, and they also, of course, add a lot of convenience. Okay. We have AI that now presents to the general public the way AI was always supposed to present in science fiction or any literature. Computers that can do anything, not by having to be a coder, but just talking to it the way you talk to another person, whether it's ChatGPT or now you can't do a Google search without taking the risk of getting an AI response, right, from latest Gemini. So these are amazing technologies, and it's not a surprise that some of the world's most valuable companies have been sinking increasing amounts of their value into making these things work. But even with all of the resources that have been invested, and again, I'm not going to rehearse the technology or the technology platforms here. Everybody knows about deep learning and the whole story behind that. But with all of the compute, with all of the data, and with all of the cost, people estimate maybe $100 billion spent on the self-driving industry, if not more, but literally billions of dollars and billions of miles driven. We have, for example, Waymo is fully autonomous, but you can only drive in some regions of just a few cities. Tesla, you can drive on any road in the United States, more or less, but you have to take over every 13 miles or so. This was from a recent test estimating that. So there's something both very compelling and also very puzzling about this scaling route, right? For the people, even the billionaires who are betting on this are honest about they can't really tell you how long it's going to take, right? It's hard to know how much it's going to cost before this actually works. And by this, I just mean fully human-level self-driving, let alone full human autonomy in a robot, let alone everything else we mean by intelligence. Or on the language model side, so this is from just a couple days ago, the latest version of Google's Gemini AI. It's a multimodal model. You can give it images, you can ask it questions. Like this is the image from that Ars Technica article, and I ask, what does it say? And it answers completely correctly. It shows the interior of a Tesla, specifically the driver's seat area, a bunch of stuff. The touchscreen displays navigation. The accompanying text is a headline and subheading from an Ars Technica article discussing the limitations of Tesla's full self-driving. Very impressive, because the word limitations doesn't occur there. And we know that it didn't look this up in some corpus or something, because this actually isn't a real Ars Technica article. I mean, it is, but I mashed up a bunch of things. That's not actually what the web page looks like. Okay. So very impressive image understanding and more like content understanding as well. At the same time, if we take something which is just a little bit out of distribution, I'm going to show you an image in a second from my colleague Vikash Mansinga from a textbook chapter. A textbook chapter designed to teach people about probabilistic programming, which is a method you'll hear a lot more from me about in a bit. But this is definitely more out of distribution, I guess, for these models. But I'll just put it up there, and you can see what it says. So here's an image. I ask, what does this image show? The image shows the CAPTCHA 52G CSLH 5CB2. CAPTCHAs are used to verify that a user is human and not a bot. Okay. I think you can all read it, and I think you can tell that's not what it says, right? What does it say? Okay, good. Do you have any doubt about that? Probably not too much. Maybe if I flashed it up for 100 or 200 milliseconds, that might be the kind of interpretation you would get. And that might be reasonable. That might be sort of the state of the art in the general purpose computer vision, although that's not what we see here, right? This is a much deeper processing thing. Maybe, again, a little bit more puzzling or also concerning, and something very different from humans, is about not just whether we make errors or get it correct, but our confidence level. And again, this is, I think, key to human intelligence. So when we ask this system, how confident are you on a scale of 0 to 100, it says, I'd say around 70 to 80%. Seems a little overconfident. Especially then, but then we get this nice justification. Well, the G, L, and 2 at the end are the ones I'm least certain about due to the distortion. I'm pretty certain about all the rest. Yeah. Okay. Now, maybe this was just a little too hard. Maybe we should have given the system a slightly easier problem like this one. Again, you can all see what's going on here, I think, right? And just literally like 5 seconds after the last query, when I asked Gemini, what does this say? It says, the image appears to be a very low resolution and noisy rendition of the word CAPTCHA. It simulates the visual challenge aspect of a CAPTCHA test designed to differentiate humans. Interesting. Again, what kind of a system would say that says 52G CSLH, and this one says CAPTCHA? When I think we can all see that this one is literally just, I just cropped down the image. It's just a subset of the other. Again, it's about 75 to 80% confident, but the general shapes of the letters C, A, P, T, C, H are there. The P, T, and the C are the clearest. Okay, so I'm putting this up to amuse us all, but really to make us ask questions, and it's not to make fun or to criticize these amazing models. It's just to ask, well, what is it that you get a pattern which is human level or superhuman in some ways, and so much not like humans in other ways? And what might that tell us about the similarities and differences of this route to building AI versus the human route? One last example. This is from some recent work that I had a small role in. I'm the last author, but I'm not the senior author. I was just the last person to join this project. Anoop Cherian is the person who did all the work here. But it's a really interesting project. This is from a paper that will be presented at the most recent NeurIPS benchmark track. It's based on the Math Kangaroo contest for kids, which is a really nice sort of set of math problem-solving activities and contests for kids going from first grade all the way up to 12th grade. This is an example of a problem for third graders from the Math Kangaroo corpus, and Anoop and colleagues made this into an interesting little challenge benchmark domain for multimodal vision language models. Since we all like math here at IPAM, this is an interesting puzzle. It's not, I don't know, is it obvious what the answer is? So here, when you put the four puzzle pieces together, they form a rectangle with a calculation. What is the result of this calculation? So I heard 15, yeah? Raise your hand if that's what you think. Raise your hand if you're still solving it. Okay. Yeah, I think that is correct. And it's interesting to solve this. You have to combine a little bit of understanding of math and a little bit of geometry, right? It's not trivial, but every one of us can do it. Now, what's interesting is when Anoop and colleagues looked at many different vision language models, first they did this with just pure language models and then language vision models. There's definitely been improvement over the years. When they started, they were close to chance. I mean, this started about 2 years ago. The latest, like GPT-4o, chances, these are like 5-point multiple choice, so chances, 20%. GPT-4o is getting somewhere between, around the mid-40s, a little bit higher, a little bit lower in some case. Humans, I'll explain a little bit more what the human numbers are because it's important. Humans are somewhere in the 60s to 70s. So, not perfect, but by this measure, but much better than chance and much better still than any of these models. The striking thing here is that this is in part a developmental test. So those human results are humans of those ages. So what you see, when it says that 58.8% or 67.6% of first and second graders got that, or humans, it means first and second graders, or 62% of third graders. Now, about 100% of you got the third grade problem right, and I think it's pretty clear. I've tried this out. We don't have the hard data on this, but that if adults who know high school or beyond level math think about these problems, they're going to get basically 100% correct on these on the earliest grade problems. Okay, at least if you try. But notice all of these models, and this is true for all of them, they're basically, regardless of whether they're better or worse than other models, they're all about the same for all the different grade levels. Very different from humans, very non-developmental in some ways. Now, we don't know exactly why that is. My guess, one reason is that a lot of these models, and I think this is especially true for like the latest GPT models, but many of the other models are really trained to do reasoning, and they're trained to do mathematical reasoning and problem solving. Some of the methods, like Kevin was talking about, are really good at like generating self-training data for learning to do like verifiable symbolic reasoning, like solving math problems. But they start with data that's more like 11th and 12th grade things. So my guess is that the training data for these models is much more in distribution for the 11th and 12th graders, and problems like these ones are just more out of distribution. But again, that's not the way that our brains work, okay? Or at least our learning mechanisms. So fundamentally, again, I guess to sum it up, the approach that's being used, whether it's to build self-driving cars, or at least their perception systems, or to build language models, multimodal models, increasingly robotics foundation models, vision, language, action models. Take the sense data, the inputs and the action outputs of the brain, the inputs and outputs, but they don't try to model what goes on inside the brain of the mind. Rather, they're just some big black box end-to-end function approximator, and you could say part of the approach is to model the input-output function of the brain and mind, but I think more fundamental is even the assumption that there is such a thing, and that is the thing that you should be approximating. And I want to call into question all of those assumptions. Yeah.
So how do you reconcile this with the use of tools, symbolic calculators?
So just hang on for that. Okay. What makes this work, and again, what makes this a reasonable bet, although one that you can't necessarily bet on, or know how much you should bet on, right, are these scaling laws. And again, I think there's been discussion in various ways about scaling laws here, including like in your talk, right? But the idea that you can quantitatively predict how performance of a deep network trained with stochastic gradient descent will improve. You 10x the compute, and you get some constant factor gain in predictive accuracy. But keep in mind, right, and this is one of the challenges for everybody in the industry and for any of us who try and understand, the predictable scaling laws are predictable scaling laws about the things you can measure, like next token prediction or accuracy on some task. But all of those are proxies, either very indirect or still somewhat indirect for the thing we actually care about. And when you have a whole bunch of power laws with different exponents, I mean, I'm sure David Wolpert can tell us about this, like, it's really hard to know how long it's going to take. It might take basically forever before before all these different power laws hit the asymptote that we want to call human intelligence. In contrast, the human way, which is really the biological way, the way of brains, starts off in a very different way. It starts off in particular this idea that inside the head is an ability to model the world. Model the world in simple ways or deeper ways that we might call understanding. So that includes honeybees, like the ones that Andy Barron told us about. I wasn't here for Andy's talk, but he said he didn't really get to talk about the world modeling stuff, but maybe we'll talk about that later. But whether you're a honeybee with a million-ish neurons, a Drosophila or a zebrafish, larval zebrafish with 100,000 neurons, so 10x less, or millions or billions of neurons, as you see when you go up through mammals and various smart birds. There is, your ability to engage the physical world and solve problems flexibly changes. But even the fruit fly, with its 100,000 neurons, has the recent computational models, neural circuits, have elucidated, for example, ways in which it has a very limited model of the world, just from its egocentric perspective, how it uses light cues, odor cues to figure out where it's going, follow odor plumes, make exploratory as well as value-guided decision-making to try to find the things that it's trying to find. And then you see much more sophisticated versions of that in famous examples of using tools from crows or chimps, for example. So human intelligence builds on all of these aspects of modeling the world, using that to link your perception to your plans, in increasingly, as maybe brains get bigger, increasingly flexible general ways. Of course, humans are different, right? These are a couple of videos. You might have seen these on in some of the, especially if you're here for the whole semester. I'll show you some work that was partly done in my lab by some former students and postdocs. But Ilker Yildirim, who talked in one of the first workshops, or the first workshop at the beginning of the semester, this is his son, just also illustrating some things that Ilker himself has studied in physical object perception and intelligence. Or you might have seen this great video that Kelsey Allen likes to show. She was also here in the first workshop about flexible tool use. A 3-year-old in an Easter egg hunt who uses a shovel in a way that probably he never saw a person use a shovel before. A person, of course, wouldn't need to get that Easter egg with the shovel. An adult could just reach it, a person, that is, an adult. When that doesn't work, he switches the object around and tries a different way. Again, not something he ever saw. It's very creative. Maybe he'd be less creative in the era of ChatGPT, but I don't know. And it almost works until his sister comes around. Okay. But you got to wonder and marvel at what's going on inside, well, all of these kids' heads. Or, in the era of self-driving cars, it's helpful to remind ourselves of this YouTube video genre, such as the one on the left, which is basically you could describe as my 4-year-old driving for the first time. So slightly older kid driving, in this case, I don't know, it's sort of like a ATV or something, but whether it's a golf cart or an actual car, or in some cases like heavy machinery or trucks, you can find lots of videos of people putting their 4-year-old behind the wheel for the first time. And you could question the rationality of the adult taking the video. But there's a certain basic rationality inside the kid's head, the ability to, again, adapt to this new situation, to take whatever capacity they had for modeling the world that evolution and learning gave them up to this point, and now deploy it in this new way, right? Out of the box, zero shot. And again, I think it's probably not based on a lot of learning from language. One more example just to show the ways in which our world models are social. See if you can tell what activity these kids are participating in. Raise your hand when you know, but don't shout it out. You'll know when you know. I'll wait till more than half of the people. Okay, now you can say, well, anybody questioning? Okay, yeah. So what are they doing? Yeah, although it's a funny kind of tic-tac-toe, right? Watch what happens in a second here. You're allowed to make moves which involve moving the pieces, yeah. And the game's about to end. Yeah, I mean, you could learn a lot by just going back and watching this, but it's so interesting that we can see a version of a game that's familiar to us. Has anybody seen this this is like a PE activity, yeah. It's a version of a game that's familiar to us, but obviously the particular board and pieces are different from usual. It's kind of this competitive race. It's a variant of tic-tac-toe. There's a lot of different things going on. It's a weird camera angle where you can barely see most of the players. Okay, but we can understand what's going on. We can understand how they can understand both the competitive and cooperative nature of it, like who's on whose team, who's competing with who. So again, these are examples of the kinds of models that evolution built us for, and that we as cognitive scientists are trying to understand. And by evolution, I don't just mean biological evolution, I mean cultural evolution, but processes that unfolded before any one of our lives, and that we inherit through both through our biology, our hardware, and the software that's transmitted to us through our experience, through language, other means of social learning. And that really just gets massively extended and amplified once language comes into the picture. So I'm not against language, and I'm just as struck by and impressed by language models' contribution to AI. It's no surprise that language models are where AGI seems to be coming from, because language is also the human superpower, right? Learning to read and write is how every child is really able to go beyond their immediate experience of the world and build models of the world by drawing on all the knowledge that has grown, accumulated culturally for many generations and maybe across many cultures, that then you don't have to discover for yourself. So this is call it the human scaling route laid out. And you could summarize it in maybe these 2 sets of 3 bullet points. I'm just trying to digest it here. The deep learning and today's AI approach and the human approach, and maybe tomorrow's AI, right? I mean, it's quite a challenge to reverse engineer and engineer this scaling route. That's what the research program is that we're working on. But just to highlight, summarize the points, I would say in the deep learning scale compute route, right, intelligence is seen as the end result of learning. It's not the start. What you start with is, in some sense, as little as possible if you follow the bitter lesson. You start with lots of data, lots of compute, and simple, especially simple, dumb mechanisms. I put dumb in quotes because it's not a critique, right? The simplicity of something like stochastic gradient descent in a neural network is how scalable it is. And, the fact that it's a simple local mechanism and all the ways it can metabolize parallel compute, really, really powerful. But the idea is learning is a simple, dumb thing, and then intelligence is the end result of learning. Okay? In contrast, in humans, intelligence is part of intelligence is what's built in from the start. It's not that adults are in important ways more intelligent than babies. Okay, probably less intelligent in some other ways, but more intelligent and key. Okay, but there's a notion of intelligence that's the real foundation that's built in that lets us learn so much more from so little. Right? I didn't dwell on the fact that language models are trained, at least the latest GPT models, maybe 100,000 times more data from language than a child gets in their lifetime. So somehow we're able to learn so much from so much less and generalize so much more robustly, partly, I think maybe chiefly, because generalization in a big neural network depends on similarity to the training data, right, is very sensitive to whether you're in or out of distribution. And it can generalize beyond distribution, but unpredictably and weakly in some ways. Okay. In contrast, our generalization is based on our models of the world, both the physical world and the social world. And our brains are designed to be those kind of modelers. And language is grounded in and builds on those models and extends those abilities, right? They're not emergent properties, but they're the designed built-in property. And lastly, on the relation between thinking and language, right? In today's deep learning systems, thinking is the thing that comes after you train on all the language data, all the residue of human thinking across thousands of years, as projected into and preserved in all the text on the internet. All that stuff contains really important patterns, the residue of human thinking, and by training on all of those, plus other special data sets that people are writing, right, and that you can get language models to write too, okay, but by training on all that data, thinking in these emergent systems, some kind of thinking emerges. In contrast, humans are thinking before language. Even before there were humans, there is thinking. Babies are thinking, young children are thinking, and language builds on top of the thinking that's there before language. And our best understanding in cognitive science is that's why we can learn language so much more quickly, because we're grounding it on top of our thinking and we're using it to extend our thinking. So I'll come back to this at the end, but in response to your question about tools, yeah, many people who've been following the left-hand scaling route said, okay, well, we got some kind of thinking through language, now let's add in some other kinds of things like symbolic reasoning or maybe some of the other things we're going to talk about and give those language models tools. But for humans, it's the other way around, right? Language is a tool. It's a tool that was only recently added to the human cognitive arsenal. I mean, amazingly valuable tool that amplifies and extends the thinking that was there before. And in the work that we're going to do, if I have time, I hope I'll get to talk about this for at least a few minutes at the end. We're using language models, and we're modeling how human language works in this spirit, right? In which language is the tool that extends a pre-existing ability to think about the world in very flexible ways. Okay, so that's the end of the first half of the talk. And now or the first part of the talk, which is a little bit, maybe less than half, yeah. But I want to get into more content and try to explain how do we capture these ideas in engineering terms. And it starts with the idea of rationality. So this is a slide from Max Kleiman-Weiner, who was one of the participants and organizers of the first workshop and part of this whole semester. He was basing this on something from Russell and Norvig, the authors of probably the leading AI textbook. Peter Norvig called this the fundamental equation of AI. You might call it the fundamental equation of intelligence, or at least rationality. And really all the computational paradigms we work on in cognitive science are some variation of this idea that intelligence, informally what I like to say is using some model of the world to make good guesses and good bets about what's going to happen, about the effects of your actions, but also about what to think about next. Okay. So here, this is just formalizing the classical idea of a decision theoretic agent that has a model of the environment that is able to predict as a function of the current state, which has to be estimated from perception, S, and actions you might take. What is the utility that you would guess would come from being in, or what state will you be in? That environment is like a transition model. What's the utility of that state? Those all might be probabilistic. So if you're computing the expected value, there's probabilities maybe on all of those things. And you want to compute the expected utility of taking different actions and then maximize that. That's the classical idea. And all the stuff that we study in cognitive science are ways of filling out this picture. What are the world models? What are the goals? They're quite rich, okay, for humans at least. Decisions and planning unfold over many different timescales. And again, I think especially for humans, there isn't just one model of the world, but we have the ability, as one of the morning talks talked about, right, to do counterfactual reasoning, hypothetical reasoning. This is important for causal reasoning, but for attributing responsibility, for moral reasoning. We have to be able to think about all the possible ways the world could have been, all the possible goals you might have. Possible, when you look back on what went right, what went wrong, who was responsible, how do you act better, who do you blame, should I blame myself, what should we do collectively better? Like those are retrospective reevaluations of the decisions and plans that we made. Okay, so humans need to have the ability to do this, and I'd say thinking isn't just, like intelligence is about having a model under this sense, like intelligence in brains is about having a model to make good guesses and bets about action and compute. But what we call thinking in humans is maybe this higher order thing where you're also constructing and manipulating the world models and the goals and the plans, okay, as structures, as structured representations in a computational sense. So Tom already advertised this new book we have coming out, which had its roots in these IPAM workshops going back 15 or more years ago. So check it out. It does present some of the math and some of the ways that we in our field have been trying to capture these sorts of things over the years. There's one chapter in here which I co-authored with Noah Goodman and Toby Gerstenberg about the idea of probabilistic programs. This is a slide from Vikash Mansinga, who together with Noah, long ago when they were researchers in my group, back again almost more than 15, almost 20 years ago, started developing a certain notion of what we called probabilistic programs. There's many things called probabilistic programming languages. There was the version that we had was embodied in something called Church, which was named after Alonzo Church. You could think of it as like a stochastic version of Lisp, but a particular way of using it to build models of how people model the world or how intelligent agents would model the world as well as make plans and so on. So it's a really powerful toolkit for probabilistic inference inside and over programs. These days, and this is reflected in this slide from Vikash, what you might call modern probabilistic programs, which is where this line of work has evolved, again, over the last 15 years or so. In Vikash's work at MIT's Probabilistic Computing Group, also Noah, for example, worked with a team at Uber AI to develop a language called Pyro. Basis, which was the organization that Kevin talked about, working on the ARC thing with Zena Tavares and Eli, who's one of the Pyro authors too, and I'm also an advisor to Basis. They're also one of the leaders in developing probabilistic programming, thinking about causal ways. But all of these methods now combine what I'd say are like the three of, if not the three, but maybe the three, best ideas that people have had across different fields for how to think about intelligence in computational terms. The original idea of symbolic languages, right, for abstract knowledge representation and reasoning. Probabilistic models, which are fundamental to making these good guesses and bets, and the combination of probabilistic models and symbols for these abilities to not just think in one world, but to think about possible worlds and think about learning that way. And they sit in these modern PPLs, as we call them, they sit on top of all the things that have made modern neural networks so great. Languages like TensorFlow or PyTorch are now JAX. And it's really exciting that we don't have to choose or fight about whether we're going to take a neural network approach or a symbolic approach or a probabilistic approach, but we are now able to explore and increasingly engineer at scale at the intersection of these ideas. So the work that we've been doing for some time in this broad view of like the Bayesian approach to cognition is really trying to use these tools and a few other tools to capture this, what I would call this developmental roadmap. So here's sort of the developmental roadmap. I'll go back and unpack this. But it's like, we want to know what's built in and how do you learn the rest. So what's built in is something that we'll call the core architecture, which are particular representations, algorithms, and goal kinds of systems there, and you can think about all of them really as kinds of probabilistic programs, I would say. And then the way we think of learning in very broad strokes, which I already sort of put out there, are like three, you could think of them as three phases, and everybody who studies development should be skeptical whenever somebody says there's phases or stages. But in broad strokes, okay, you can think about learning as like the first 0 to 1.5 years, which is learning inside this core architecture, much of which is grounded in the brain architecture and shared with other animals, though human brains are different, but much of it is shared. Then, but it's learning before language. 1.5-year-olds already know some language, but they're not using language to learn, and they don't know a lot of language. They don't really have conversations. But between 1.5 to 3, that's where the key language learning happens, so that by the time you're 3, you're able to have a conversation, even to a very simple one, like to ask why, and to want to ask why. And when your parent responds, you may not really understand each other, it may be a little frustrating, but you understand just enough to get a bootstrapping loop going so that you can really start to learn about things you can't directly observe or understand, except now through language. And so that's the last phase of learning, more or less, which is from age 3 on up. Of course, there's more, but basically using language to learn everything else, including new languages like math and programming and so on. Okay, so that's sort of the broad thing we're trying to do. And we're using probabilistic programs as a toolkit here. We're also using, the slide I flashed through quickly, what we could call the game engine in the head. So these are particular kinds of programs for simulating the world. Like, for example, this is one of the popular Zelda games, based on modern video game engines, have tools not only for real-time interactive computer graphics, but simulating really interesting physical worlds like this one, where there's objects, there's gravity. In many ways, it's just like our physical world, except there's various kinds of magic or science fictional powers and abilities. You can jump and fly. Things can make other things explode or stick. Right? You might think of these as almost like kind of metaphysics, in that they don't follow the actual physics of the world, but the higher level, like hypothesis space of possible ways physics could be. These are programming languages that let game designers express possible kinds of physics. And by doing inference and learning in that kind of a physics world model, that's a really powerful way to capture, let's say, our intuitive physics. Analogous things on the theory of mind side. And we also, I'll show this a little bit at the end, but we also are using language models, especially code LLMs, but we're using them as ways that we think language is a tool for humans, namely as a tool for doing what we're doing right now, communicating thoughts. I'm saying some language, you're hearing some language. In the question period, we can go back and forth. But one way to think of that is using a language model, or using something like a sequence-to-sequence model, a translation model, going back and forth between a set of symbols that we could call English and internal languages of thought, such as a probabilistic programming language. So that's the way we use language models, and we use that in a way that we think reflects more the way humans use language. Okay, so that's the end of the second part of the talk. Sorry, I don't actually have an outline slide to follow. And now what I want to do is get more specific and show you the way we use these tools. So I'll just say a little bit about intuitive physics, mostly because I'm going to come back to it at the end with language. But so the people who've been here all semester, or who've seen me, I talk about this a lot, so probably many of you, if you've seen me talk before, have seen me talk about examples like these kinds of things, where we might ask people, to capture the basic kinds of physical world modeling that perception gives us, that our plans operate on, and that early language grounds into. Questions like taking these stacks of blocks, like think of them as like Jenga blocks, we show people a whole wide range of different scenes, some of which look very unstable, others of which look very stable, and ask, for example, how likely is this stack of blocks to fall? Or if it falls, which way will it fall? Or we might ask a sort of a much weirder question, like the first question is the kind of thing that any kid who played with blocks, or anyone who's played the game Jenga has thought about many times. So you have a lot of, let's say, experience on that. But we could also take a scene of blocks with these red and yellow blocks on the table and say, ask a kind of a hypothetical. It's not exactly a counterfactual, but a hypothetical. Suppose that you were to bump the table hard enough to knock some of the blocks onto the floor. I'm not telling you how many, so in that sense, there's some uncertainty or vagueness. What do you think? Will you knock off more red blocks or yellow blocks? And again, we can get graded judgments for likelihood of falling or likelihood of more red versus yellow. And we get data and model fits like this. So I'm just giving 2 examples of the results from an experiment that we might do or have done, where on the y-axis we plot the average judgments on the question that a group of people make, with error bars. On the x-axis, we plot the average predictions of our model, and it's the same model, more or less, behind both of these things. What the model does is it reconstructs an inference of the 3D scene, something like basically a percept that is the state of a game physics engine. It's very similar to like a CAD model, but the objects have a small number of physical parameters. And then that's only a guess. Okay, you make a guess because you can't perfectly see the 3D scene from one image, but you can get a pretty good guess as like a Bayesian posterior from a probabilistic inverse graphics program. I guess I didn't explain this, but this is the probabilistic program over here in the lower left, where you see an image, and perhaps images over time if it's a movie, and you see the image as the output of a graphics program. You put a prior over the possible inputs, which are these object-centric CAD-like scene descriptions, and you make an inference. What are the likely inputs to the graphics thing that would have produced the output, that is the image? Okay. And then that same inferred world state is also the state of a physics model, which we use one of these game-style physics engines, where we can quickly run a small number of simulations. Like here's one simulation of one of these table bumps on the red and yellow scene. Here's another simulation, same table, just harder bump. But the point I want you to get from this is that it doesn't really matter whether you bump it hard or light. In our simulations, we do a small number, like 5-ish simulations. And just to capture the kind, at the grain of intuitive physics, at the grain of actual physics, it matters what's going to happen. But in each of these cases, all the yellow blocks went over, few of the red. So you just take the average of a small number of those simulations. And also, they can be quite short simulations. Notice you only have to run a few time steps to know what's going to happen. They could also be very coarse-grained simulations and noisy. And those are all things that we and others have been exploring. Okay. So just a small number of potentially noisy, coarse-grained simulations run for just a few time steps may be a reasonable way to capture, in this case, our sense, the guesses and bets we might make in a physics setting. And with a number of students over the years, including some who you actually heard from all these folks in the first workshop, Yildirim Allen, this is Kelsey Allen and her virtual tools game with Kevin Smith, and Toby Gerstenberg, who showed you work. And if I'll just call back to the videos. They're really great talks, much better than I could do in this talk. So if you're interested in these things, if you want to look at Toby's talk to see how we use counterfactual probabilistic simulations to capture people's sense of causality, as well as responsibility attribution, both in a physical sense, what was responsible, like in the Billy and Susie case you heard about, for breaking the window, but also in a social sense, when agents are working together, how do you assign responsibility or blame when something doesn't work? Kelsey and Kevin have looked at how you use a small number of simulations in a probabilistic physics engine to solve interesting new tools challenges that you haven't solved before. And Ilker, go back and watch his talk, showed you how you can do many, many interesting things, including making inferences about rigid objects, non-rigid cloths, fluids and liquids, and how all those interact in perception and in your predictions. I'll highlight one thing that didn't come up in the first week, because it does say something about learning and what learning looks like in the first stage of cognitive development. So I'll show you data from adults, but we're modeling adults in a setting that we could also study kids, like that one there, like that air hockey table, this is work that Tomer Ullman did with me a few years ago. Tomer is now, or I should say, Kelsey is just finishing up at Google DeepMind and is starting a faculty position at UBC Canada. Ilker Yildirim is at Yale. Toby Gerstenberg is at Stanford. So if you're looking for students or grad student positions or postdocs, or you should seek them out at those places. They're all awesome. Tomer is at Harvard. And work we did together some years ago, we showed people scenes like these ones here, which is like looking down at an air hockey table from above, and you're seeing these different colored pucks. In each case, you're seeing just a 5-second movie clip of how the objects move, and then it's repeated over and over. And you'll see in different situations, there's different kinds of underlying physical laws. So sometimes you'll get the sense that some kinds of objects attract or repel each other. You'll also get the sense that some kinds of objects are much heavier or lighter than others, and perhaps that some of these patches on the surface are rougher or smoother than others. Okay. And in experiments, we ask people to watch these 5-second clips. They can watch them as many times as they want. Usually they watch them 3 or 4 times. And then we ask them to make judgments about all these physical properties. And here we're now showing the predictions of a model of a hierarchical Bayesian inference model with their judgments. People are not super accurate in this task. This is a hard task to judge like all these different physical things from 5 seconds of video, even if you can watch it 3 or 4 times. Okay, people are not that accurate, and our models do not fit them perfectly well. That's really important. But what's interesting is that still they're well above chance, and our models capture the main trends in people's judgments, including some qualitative patterns of errors they make. So there's interesting like illusions where they systematically mistake certain kinds of forces for others, and the models do the same kind of thing. And the way it works is just, again, sketched here. This is what's called a hierarchical Bayesian model, or you could think of it as a hierarchy of probabilistic programs. The meta theory, or the metaphysics, if you like, is just sort of like the general idea that there are objects and they can have forces. We might assume something like F equals ma, but there could be, there could be different kinds of forces. And then the specific theory is like what forces are in play. Is there something like gravity? Is there a wind blowing things this way or that? Are there forces of attraction or repulsion between different kinds of objects, different masses? So this is like the theory of the actual world. On the top is the hypothesis space of possible worlds. And then for any one of these different force laws, there's a set of traces that capture different scenes that are going on there. Okay. So the point I want you to get from this is that by doing probabilistic inference in one of these hierarchical structured models, we can capture how people are able to learn these various parameters of the particular physics that they're in extremely quickly. Many people in machine learning wouldn't call this learning at all. You just call this inference, right? There's no like offline training, although the models are accelerated and become more human-like by finding certain patterns in the data. But it's not a neural net. It's just very simple like motion heuristics. Okay. And that's not an essential thing. It just makes them a little bit better, but it's nice. Okay. But the key is that, again, by having the right kind of structured architecture, you can learn very quickly and very robustly, well outside of the distribution of actual physical experience. Since we don't have too much time, I'll just point to a whole other line of work where you take the same kind of idea and you apply this to basically trying to look at agents moving around. These are examples from experiments done with infants, again, really prior to learning language, like 1-year-old infants, who might see these scenes and not just see a blue and red ball moving on a table, but one thing chasing another and the other trying to run away. Or seeing this little red entity here jumping over a wall to get to a blue one. And then the height of the wall will vary, and depending on how high or low the wall is, and whether the red agent jumps or doesn't jump, you make an inference about how much the red thing likes the blue thing. Basically, even 10-month-old infants will make the inference that if you are willing to jump over a really high wall for someone, you must really like them. Whereas if you don't jump over even a little low wall, not really your friend. Okay. So the way we model those kinds of things is what's called Bayesian inverse planning. And I put a whole bunch of people's names on these slides because over many years, with a number of students and colleagues, we've been developing these models and really applying them to many different situations, not only this kind of situation here, but many others. But the idea is you observe actions that an agent takes, subject to whatever the physics of the environment are, actions that may change the state of the world or the agent state, and then you infer all the stuff in the middle. The beliefs and goals, like the desires to be with someone or to catch someone or to get away from someone, and the beliefs about how hard something might be or your physical constraints or your own strengths, those are all have to be inferred because we don't directly observe them, but they can be inferred as the probabilistic inputs to a planning function that produces the actions and then feeds back, changes the state, and then also has some perceptual inputs. So you're making inferences about the belief states that are the outputs of perception, and that together with the inferred goals best explain the observed actions. And I'll just point you to work of all these folks, but including, like, for example, Tan-Chi Shen, who's also on the job market right now, who used this to really show that you could really capture, almost too accurately, honestly, many intuitions that young babies have and that adults would have. This is the baby intuitions benchmark, which really does, again, much better than just like a generically trained model, like a visual transformer, for example. Work that Tao Gao, who's a professor here at UCLA, did for understanding social interactions, using these models where you could model, for example, like what it means for one agent to help or hinder another agent by having a recursive utility function to say, Like, it's not just that I'm trying to maximize my own utility, but if my utility takes as input a positive or negative component of your utility, then that's a way to very abstractly capture the notion of helping or hindering. And you can infer the coupling between agents' utility functions by observing their joint actions. These are examples from Tao's work of, Tao's the guy in the foreground here, as well as the guy in the chair, kind of unusual out-of-distribution helping interactions, as well as some competitive things. That's Tao's wife there, and they are friendly, but in that scene, her job is to try to figure out what he wants and defeat it by getting to it first. Or Max Kleiman-Weiner, who I mentioned before, has used these models together with others for what he called theory of minds to reverse engineer cooperation. So you're making inferences about who's working with who in a group setting. Or Sidney Levine, together with Shen and Zhou Quan, have used these models to capture really interesting kinds of moral reasoning, like when is it okay to get out of line, for example. Okay, so I'm giving you a sense of the various ways that we have worked on trying to capture both the core architecture and some of the ways that like kinds of rapid learning can work in that core architecture. Kevin Ellis mentioned some work that he was doing, the world coder work, which built on and was at least partly inspired by Pedro Savidis' EMPA stuff. I don't know if anybody here else knows about EMPA, but it's really cool work. You should check it out because it brings a lot of these ideas together. In this case, to learn new world models within a core architecture of a simple kind of video game engine. So Pedro showed that you could give people these relatively simple but Atari-like video games, give them a game engine representation that could capture all the different ways these games could work, and capture how people can learn these games extremely quickly. So people can learn these new games in just a couple of minutes, maybe like 1,000 steps of the game, and these models are able to do that. Very, very different from like the deep reinforcement learning sort of thing. Okay, so what about how do we learn beyond the core architecture? So I think I have 5 minutes left, as Sumit has informed me, and about half of my talk. So I will. It's fine. Because I talked about language and everyone wants to know about language, I'll do the last few minutes on language. And the part that I'm skipping in here is earlier work that Kevin did with us on Dreamcoder, but I think a lot of people know about that. I'll just say that in Kevin's beautiful talk, when among other things, he showed some of the ways that like the idea of like library learning, like learning, for example, this beautiful stuff that he did, or that we did together in the Dreamcoder work, learning, for example, these logo drawings, learning to do these drawings by learning new kind of program primitives like a library of logo graphics, which we did in a sort of developmentally inspired way by bootstrapping from simple problems that you could solve initially, like these little drawings there, to bootstrapping a library and a wake-sleep learning where you use the learned library to generate more training data for a neural network. In some ways, you might say, I don't know if this is how Kevin would put it, or I think his paper like very wisely considers the ways in which this is true and not so true. Like maybe if our goal is just to have AI that can solve these problems, maybe we don't need to do any of that library learning because we already have Python. Python has all sorts of great functions and libraries. But we still need to do some wake-sleep learning, but we may not need to do library learning. But I'll just say that from a biological point of view, library learning and learning without language is still well in play. And just advertise some work that will be coming out soon, or this is from a really great postdoc, Lucas Tian, who also worked with Kevin and me on basically like applying Dreamcoder to humans learning to draw things. But now he's working on monkeys. And it turns out, again, you don't need language to learn symbolic vocabularies for drawing, whether it's compound shapes like that or these other shapes here, where basically the monkeys are drawing, they learn, like you see how the monkey draws on the touch screen all the circles and then he draws the lines, right? So the monkey has learned a simple kind of syntax or grammar, which is basically first he's learned primitives like circles and lines, and he wasn't taught them, he just learned them because they were efficient ways to put ink on the page. He was just reinforced for getting the ink, for covering the pixels. But then he might be taught, like, okay, he's only going to get reinforced if he covers all the circles and then the lines. Or on another day, it might be all the lines and then the circles. And Lucas is doing this because he's also recording from basically the entire front of the monkey brain on both sides. He has, I think the technical term is a lot of electrode arrays. I think it's 16. So we can study the neural dynamics behind this. But this is Lucas here, and in this really cool joint project, he's shown again that basically monkeys can learn these abstract principles, like simple grammars, from just trained on 1 or 2 lines and circles, but then they can right away out of the box generalize those patterns to 3 lines or 4 lines. So it's very simple stuff, but it's showing that the ability to learn symbolic primitives and to put them together flexibly into higher order structures, one day this, one day that, is not just a human thing, but is an ability that is some basic part of the brain. Okay, but as I said, and I'll just come back to this for the last few minutes, language is special, right? Like the ability to learn programs, whether it's through a large language model or maybe even a small language model, but especially a model that somehow can translate between natural language and code, I think really is part of the human scaling route and not just a scaling route for AI. But in the human tradition, we think it can be done with a much smaller language model, one that could be trained with the amount and kind of data that humans have. Okay. But that might include code, not necessarily in Python, but code in one of these languages of thought. So the last work I'll talk about is this work from Leo Wang and Gabe Grand, and many others, also Alex Lev, Vikash Mansinga, Noah Goodman, and Jacob Andreas are all PIs on this as well. It's described in this paper that's on arXiv called From Word Models to World Models, translating from natural language to the probabilistic language of thought. Okay. And the translation part is important. The framework that the paper describes is also the name for our framework we call rational meaning construction. The rational part is rational in multiple senses. It's rational both in the sense of that I've just talked about, which is that the meanings are basically these probabilistic programs, so rational models of the world and expected values. Okay, but it's also rational in the sense that Tom Griffiths talked about, especially resource rational. Namely, we're making arguments for and having some demonstrations that code LLMs, even very small, relatively simple, like you wouldn't even call them large language models. Like in this work, we initially used OpenAI's Codex model, which today we might call a medium to small language model. It's much smaller than GPT-4, but it was trained on a lot of language and a fair amount of code. And you can use that as a way of translating from various things you might say, both specific and generic in natural language, into world models, both the questions, the conditioning and questions that you want to use those models, but also the models themselves. So I'll just to illustrate this a little bit in the physics setting. So for example, if we go back to these kinds of settings where we say, based on evolution mostly, and maybe a little bit of learning in the core architecture as young children, we have this powerful ability to think about these physical scenes, to perceive them, to imagine what might happen. Now, one way to add language into the picture is to ask you to imagine a scene. I'm not going to show you the scene. I'm just going to describe it in words. So I can just say to somebody, imagine I have some red blocks and yellow blocks stacked on the table, and I bump the table hard enough to just give you that same question. But now I use language to describe the scene. And across different trials, I might say, well, there's one tall stack of red blocks, and there are 2 short stacks of yellow blocks. There could be vagueness in this. I don't necessarily say what tall or short is. And sometimes I might say there are a few red blocks, or a bunch of small yellow blocks. So there's both precise, like quantities, and also imprecise, vague terms. And then we have a model that will model your judgments about how you answer that question by translating that English into code in a probabilistic programming language. So these are conditioning statements that basically set up this simulation that you can then run in your head, in the model's head. So this is now a 2D physics engine simulating that same situation. This is not, again, nobody sees this, just as like looking inside the head of the model, the simulator that it's set up. Okay, so somebody might say, in AI, if you like language models, you might say, oh, we're giving a physics engine and some probabilistic inference as a tool to the language model. But we would say, no, we're giving a system that started off being able to imagine and make inferences and predictions about the world. We're giving language as a tool to allow it to think about scenes it hasn't seen before. Okay, here's a more complex scene. And whether across simple and complex scenes, I'm now showing you the same kind of scatter plot from before. The model is able to do pretty well. This was like quite striking, I should say, by the way. This is work that Said Zhang, who's the first author here, did as part of his first-year project in grad school. He did this, I mean, again, credit or maybe whatever you want to put for a first-year grad student doing a class project. But he did this project in like a week or two. But it's a credit to, I think, that the ideas and the infrastructure and also his hard work was that he was pretty much able to just get this thing to work out of the box. It was very quick, and it's a tribute to again, the fact that these language-to-code models it's pretty easy, there's a little bit of prompting, but it's pretty easy to get them to write code even in a language that they're not expert in, a probabilistic programming language. But then what we're really exploiting is the modularity of language and all this other stuff that we've built in our group, recapitulating much, much harder work from evolution and development, building like probabilistic simulation-based mental reasoning. Okay. The last thing I'll show you with this is I don't know if people know the Bayesian tug of war, but it just, I will stop in just a minute, so just indulge me for one more minute. But because I think it's really, this is the last key part of the scaling route, which is that what I showed you there was using language to now describe a world that you haven't seen, but the simulator was all built before. Okay, but we can also use language models and probabilistic programming languages to do maybe the most remarkable thing that people do. And these are just demos. There's no quantitative valuations, but it's work that we're in the middle of doing together with both the people I mentioned, but also with Katie Collins and Tyler Brooke Wilson and a number of others. But the idea here is to say, take advantage of the ways or model the ways that people talk to other people using generic language. Like, we don't just describe a particular scene, but we say, if you drop something, it'll fall. Or, planets go around the sun, or something like that, right? Ice can melt. Metal is a lot heavier than wood. Things like that, right? So we can take generic statements like that and turn them into a world model that can now be deployed in a scene, even if you don't really know how to imagine those things. You can, because you have a symbolic language for building probabilistic models of the world, you can do this. So for example, there's a domain that's somewhat of a classic one in the probabilistic language of thought literature, what's called the Bayesian tug of war, where we describe in words the way like teams of players might play tug of war and how the outcomes might depend on the player's strengths, which could have a lot of uncertainty, and also whether the players are trying hard or are they lazy, and the team that pulls the hardest is the one that's likely to win, but that depends on how strong the players are and whether they pull hard. And what we can do is we can translate in a sense, the world model of what the tug of war domain is like. We can produce a probabilistic program, this is in the language church, where our language to code model wrote all these things. So it used to be that when we first started working on these kinds of world models and probabilistic inference, Toby Gerstenberg was the one who first did these things with Noah Goodman and me. We wrote all the model code ourselves to capture what we thought people were getting in their heads from when we gave them language. But now the system can write that code itself effectively, and it can do it prompted in a very limited way. In this case, we're just prompting it with like one example of a probabilistic program together with language annotations. It's really it's like the most minimal prompt. It's a medical scenario. But that's enough to be able to take English. It's again, I don't. This is just a demo, but I don't think that's the only thing you're going to need. But a prompt of just a few models like that are enough to basically get a system that can now write the code in a probabilistic programming language for a new model. You can even, again, this is, work in progress, but we can even say, well, maybe we can, and this is the sense in which maybe we're using language at its most powerful. We can give maybe, let's say, a few different models, like a medical system, a medical domain model, thinking about students and tests, maybe thinking about the tug of war domain, and describe some other kind of situation, one that's not so different from a tug of war, like a relay race situation. But you might think of what's going on here as like a very high-level sophisticated analogy, where we are describing some interactions, various outcomes of races and so on between a bunch of people, and the system is able to write a probabilistic program that does at least a sort of reasonable job of modeling this domain. It's not the best we could do, but it might be an example of the kind of model that a person who's not an expert racer might build in their head by analogy to other systems. So again, it's prompted with examples of domain models, including natural language to code translations. And then the system now we're not giving it the background knowledge, but it is coming up with its own background knowledge that then lets it reason about new situations. Okay, and then actually you can run probabilistic inference and compute like how likely do you think it is that somebody's strong or weak or tried hard or not. Okay, so that's all I'm going to say. And thank you for letting me go on just a little bit. But what I hope you've seen is at least both a lot of work we've done over the years that's pretty solid to capture some of the earliest stages of this scaling route, but also where we're going beyond this, including like how we get to more long-range kinds of actions, social interactions, but also especially all the ways that people learn not just from their direct experience, but by using language, which really is a superpower, but grounded on and amplifying and extending the intelligence we have before language. Okay, thanks.